All right, so we'll get started. We're starting a few minutes here past the hour, but please grab something to eat. We're going to conclude the AI-SDM seminar series for the spring with a bang today with a high-impact speaker. We have with us today tenured Associate Professor Aaditya Ramdas from Statistics and Data Science and Machine Learning here at CMU. He's moving onwards and upwards, so glad to have you here with us today. Aditya has won a slew of early career awards, probably too many for me to name, but including the Career Award from NSF. His work has also been recognized by the Presidential Early Career Award, and he was recently recognized with a prestigious Young Alum Achiever Award from his undergraduate institution, IIT Bombay. Currently, he's a program chair also for AI Stats 2026. And in addition to those responsibilities, he's also has a new member of his family. So congratulations, Aditya. Sure, lots of things are keeping you busy right now. And he's been a key contributor to the foundational work in AI-SDM. So congratulations on your continued success, and we look forward to your talk.
Thank you very much. Thanks, Ron, for the wonderful, kind introduction. Thanks, all of you, for being here. This is only the second time that I'll be talking about this work, so I'm very happy to see a nice and varied audience here. Not people I usually speak to, so it's nice to see all of you. So I'm going to be talking about Changepoint localization. Very easy to define problem. I'll define it soon, and a particular angle that we're going to take at it, which gives the conformal to the title. It's actually a tale of three papers. Unfortunately, the first two ended up being what I would now call, in hindsight, the wrong answer. Somehow I had to go through the wrong answer before ending up at the right answer. So I'll only talk about the right answer today, not tell you about the whole tale, which is the last work, which is joint work with my postdoc, Rohan, who's sitting over here. So so that's just, it's an archive if people are interested with that same title, and it's in submission. So I'm happy to hear any feedback because I can still incorporate it. Okay, so here's the backdrop. So most data analysis methods have been historically designed for real value data, categorical data, things like that. They're usually not well suited to directly handle images or text. But modern AI and machine learning methods can handle these more complex data types easily, but they're mainly focused on prediction performance, not on rigorous uncertainty quantification. So a more general question that has motivated one line of my work is, what kind of general principles or methods allow us to leverage these powerful AI ML methods, but for rigorous inferential problems? And a few years ago, I talked about conformal prediction from a completely different context. And today we'll see how to use some of those ideas for a different problem, which is Changepoint localization. So the motivation for Changepoint localization and Changepoint, hopefully people understand what a Changepoint means. It's like there's a system that's performing one way that you're monitoring, and then after some time it changes, and you would like to detect that change, but you'd also like to know when that change happens. So it's actually, most of the literature has typically focused on Changepoint detection, which is just tell me that there has been a change so that I can go and monitor it, fix my system, whatever it might be. The difference is that, like in what we'll talk about today, Changepoint localization is I want to know when the change occurred. Okay, and so knowing when a system changed often matters more than just knowing that it did. Okay, so for example, if you're automatically monitoring, of course, some equipment in a big factory, and you have all sorts of sensors, you might want to know that something might have failed, but you might also know when did that start to occur. Might help with problem diagnosis. If you're looking at sentiment analysis over your restaurant, maybe you have restaurant reviews coming in, and it's a popular restaurant, and then suddenly there's a change and people don't seem to like it anymore. Maybe you'd like to know when that change started to occur. Or this could be Amazon reviews, things like that for your product. Or in financial markets, when did a trend change and so on. So that's the motivation behind moving past detection to localization. Yeah.
So if you do a binary search where you repeatedly apply Changepoint detection, that is good baseline for localization?
No, it doesn't give guarantees. Yeah, I mean, you want, I'll define what the problem is soon, but you see detection won't directly give you that. Yeah. And so existing approaches, which I won't cover in any depth, But I'll just tell you at a high level what, even for localization, people have studied localization, but there are many drawbacks to past works. So there's the first class of works are what are called parametric type methods. So likelihood-based methods, they often involve making some strong modeling assumptions about the type of data that you're seeing. And they often require disjoint, sometimes pre and post change families, things like that. And if the issue is that if it's really misspecified, then it's not going to work very well. And if you're dealing with complex image types, usually parametric methods won't work well. So there are non-parametric procedures, but they often only attain certain types of asymptotic validity. And in practice, when you want to implement them, there might be some unknown constants or loose constants that you have to use. Not very good. And then there are what are called resampling, like bootstrap type methods that people have come up with, but they don't offer finite sample guarantees and actually are sometimes computationally expensive. So what we're going to do is try to address all of these drawbacks of past work and our work. We want it to be model free, our methods to be model free. So they should be non-parametric. They should be non-asymptotic in the sense that I really, if I ask for a 1 minus alpha guarantee, which I'll define soon, I really want to get it in finite samples. And most importantly, I'm especially when dealing with images, text, things like that, I don't want to make distributional assumptions on my data. So a key term that will reappear throughout the talk is distribution free. It basically means giving guarantees without making any distributional assumptions whatsoever. Okay, so here's how the outline will go. I'll present the problem statement, which is extremely simple to understand. And then to convince you that this is worth listening to, I'll show you some experiments. The method that we propose, apart from being distribution free and non-asymptotic, works excellently in practice, kind of out of the box. And so I'll show you some real experiments to convince you that it works really well. Now, after I've convinced you that it works well, I'll tell you what the algorithm is. So the third part of the talk is just presenting the algorithm. It's also an extremely simple algorithm, luckily. There'll be a key part where the user has to play a role, which is choosing a score function. And so we'll then delve into a good choice of score functions, which will be motivated by a result which we call the conformal Neyman-Pearson lemma. And then we'll end with some more experiments later on. And to be clear, all the experiments were run by Rohan. So if we have further questions on some of those experiments, I will smartly defer to him. All right, so here's the problem statement. So it is distribution-free change localization. So we are given an ordered data set, x1 to xn. And here the important point is xt lies in any space script x. So xt could be an image, it could be a piece of text, it could be real value categorical, I'm not going to care. So you have just some general space over which you want to detect changes. And the situation is as such, you have, I'm going to call the change point as psi, okay? And so you have x1 to xi, which are marked in green, and xi to xn, which are in xi plus 1 to xn, which are in blue. Okay, and the idea is that you want to identify xi. Okay, sorry for the slight overlap there. So we're going to assume, so this is what distribution free really means. We're not going to assume that we know anything about the distribution of the green part and the blue part, apart from insisting that they are exchangeable. So informally, maybe if you're not used to thinking about exchangeability, think about the IID setting. You have x1 to xi, which are IID from some distribution which is unknown. I'll call it P0. Xi plus 1 to xn, which are IID from some other distribution, P1, which is unknown. Okay, and P0 is just not equal to P1. They're just different distributions. This xi is just some number between 1 and n. And if xi is n, you can think of there's being no change. If it's between 1 to n minus 1, then there actually was a change. And what exchangeable means, at least, formally what it means is that the joint distribution of those data points is invariant to permutations. So x1, x2, x3 has the same distribution as x2, x1, x3, and so on. And IID is a very simple special case of exchangeable. So if you're not familiar with exchangeability, you can just think of it as IID from some distribution and IID from some other distribution. And the key point of what distribution free means is that we're going to not make any assumptions about them. They're just completely arbitrary and unknown. Okay, so and now what we want is, given a confidence level alpha, like 0.05 or something like that, we want a 1 minus alpha confidence set for xi. We want a set of indices that covers xi with high probability. So formally, what is that? It is a set. I want you to output a set C. C is going to be a function of the data. The input is x1 to xn, and C is a function of x1 to xn, and it's just a subset of 1 through n. Okay, so I'm going to output a set C such that the probability that psi is in C is at least 1 minus alpha. So C should contain my true change point psi. That's what it means to localize it. I give you a confidence set and I say with high probability the change occurred here in these indices. And I would like this guarantee to hold without making any distributional assumptions. And this peak psi means that the distribution of the data is coming from the setting where psi is the true change point. So peak psi means when psi is the change point, I would like psi to be in my set with high probability. And psi itself is arbitrary and unknown, P0, P1 arbitrary and unknown. So it's very, like it seems like a grand goal, which is how can you possibly produce an informative set C without making any assumptions on psi or the distributions? How is it possible? But remarkably, this is possible. So and in pictures, this is what we're looking to do. So let's say you see some data, which is the data in blue, and the true change point in this simulation is marked in the dotted red line. The hope is that we're going to construct a green region, which is our confidence set, which says basically, well, we think that the data is in this region with high probability. Okay, the change is in this region with high probability. Okay, so two examples. Okay, just to start out with, so one with images and one with text. So MNIST and sentiment change. So here we have a sequence of digits, and they are ones up to time 400, and they are sevens after time 400. And what the plot is showing you, and we're going to I'll explain the plot because we're going to see many such plots going forward. Is on the x-axis is the index. There's 1,000 such images, and 400. The red dotted line is actually the true change, and on the y-axis is actually a p-value. So what we're going to do is we're going to, and I'll explain it again later. We're going to test: is the change at 0, is the change at 1, is the change at 2, is the change at 3, whatever. We're going to just test for every point is the change there. And we'll construct a p-value for each of those. And so the p-values are being plotted over here. And what this flat line very close to 0 means is that we are very confident that the p-value, that location is not the change. Okay. And there's actually only one kind of spike here, which is close to 400. It's very hard to see, but there's a blue spike at 400 or just around it. There's a spike where the p-values become large. And so it will turn out later on that the confidence set is actually the set of indices for which the p-value is larger than alpha. So in this case, alpha is 0.05. That's the green dotted line. And the confidence set is the set of indices for which the p-value is larger than the green dotted line. And in this case, the confidence set is super tiny, around 400. Okay, so this is just an example to show you that the method works on generic data types, and it produces sharp confidence sets. Just a different example. I think I might do sentiment analysis later on, but this is a different example of images, maybe slightly more sophisticated than MNIST. But basically, there's like 1,000 images, and at time 350, it changes. Like the first set of images are real images, and the rest of them are sketched images. And so there's like a domain shift from the real to sketched images. And so the method just gets in a sequence of images, and in this case, it produces this p-value plot, which actually the confidence set is super tiny around the actual change. And so, now let's get into this. How is the method working so well on this type of data, and how are we leveraging? I mean, of course, you still have to leverage machine learning methods and classifiers. So here there was a CNN that was trained on 2 out of the 6 classes in this data set which is called domain net, and we just converted from RGB to black and white so that because sketches are in black and white, we don't want the black and white to be the differentiating factor between real and sketched images. So it really had to learn something about something more than the color to differentiate between them. And so, but we still had to use a CNN under the hood. The question is, how do I use? So in the previous case, we had an MNIST classifier. Question is, how do I use an MNIST classifier which was trained for prediction to do change detection instead? How do I use a CNN for prediction, trained for prediction? How do I use it for change detection instead? So that's or change localization instead. Okay, so hopefully I've convinced you that the method is works pretty well. So now let me tell you what the algorithm is and formally describe its guarantee. It's a very, very simple algorithm. And before I tell you the algorithm, I'll give you some intuition about how the algorithm is derived. And because if you've not seen conformal prediction before, it might seem a little magical. Where did this come from? So the basic ingredient in the algorithm is going to be what's called a conformal p-value. And if I had to summarize what a conformal p-value is in English, it basically is the idea that sequential ranks on exchangeable data are IID uniforms. Okay, so I mean, so it's a variant of this idea that will come up in conch in our method. But let me explain a little bit like what conformal p-values are. So forget the setting that I described of a change location. Just assume that you have a sequence of, let's say, IID random variables, okay, or exchangeable random variables, but IID random variables. And now let's compute these things called sequential ranks, which means what is PT? PT is the rank of the tth observation amongst x1 to xt. Okay, so in this case, so what is rank? I'm just going to count how many are less than xt and how many are greater than xt. Let's say right now these are real valued random variables. And then there's a uniform, just to break in some sense, to smooth out ties, there's a uniform random variable ut that's independent of everything else. You should think about this as going from a discrete uniform to a continuous uniform, or smoothing out ties. So we are calculating a rank of xt. Now the interesting thing is that if the data are IID or exchangeable, then the last observation, like the tth observation, is equally likely to be any rank between 1 to t, because they're all, the first t observations are IID, so the tth one is equally likely to be rank 1, rank 2, rank 3 to rank t. And so the claim is that PT itself is a uniformly distributed random variable. But beyond that, actually more than just PT is uniform, actually P1, P2, P3, the sequence are marginally uniform, but they're also independent. They're actually IID uniforms. So the rank of the tth observation among 1 to t is actually independent of the rank of the t plus first observation amongst 1 to t plus 1, which is independent of the rank of the t plus 2th observation among 1 to t plus 2. So it's, if you think about it, it's very natural. If I told you that amongst the first 5 observations, the 5th one was the largest. Now I ask you, amongst the first 6 observations, what's the 6th one? Well, actually, it's equally likely to be any of the 6 ranks. So this is an interesting transformation to go from data to ranks, to in fact uniform random variables. And the reason it's useful is because, okay, suppose x1 to xt are, this stream is not real valued. You can apply a score function to transform them to real valued and then calculate ranks. And so now you've basically taken something from some domain to something that has a known structure like uniforms. So these conformal p-values, they're actually used implicitly in conformal prediction. Hopefully people know conformal prediction by now. I think when I gave a talk about it a few years ago, maybe less people knew about it, but now it's really in pretty much all conferences, there are papers on conformal prediction. It's being used in many practical settings. But these conformal p-values lie at the hood of, under the hood behind conformal prediction, and they lie under the hood of what Wolf calls sequential tests for exchangeability, where you can actually test if your data is IID or not. And so now we're going to adapt these ideas to instead localize a change point instead. So what this is the key, this idea is kind of independent of the change point localization problem. You can just appreciate that idea independently of today's talk. That's kind of why this slide exists. But here's the overview of the actual conch algorithm. So, we have this, have some pre and post change. And as I said before, for each t, we're just going to test the hypothesis that the change occurred at t. Okay. And then once we test each hypothesis, there's a standard duality between testing and confidence sets, which says the way you form a confidence set is just you return those tests that did not reject. So essentially you test at level alpha, and if you did not reject at level alpha, you can include it in the confidence set. So we'll first test every index, and then after that, the confidence set is trivial. It's just a set of indices for which the p-value is larger than alpha. And if you really want a point estimate rather than a confidence set, then you can just return the index that has the largest p-value, and that's a sensible point estimate as well. So the conch algorithm takes 2 things as input. So the first thing is a score function, a change point plausibility score function that's going to be denoted S. It's just some function that takes in your data xn and outputs a vector of n-1 real values. Okay, and so you should think of this is where the machine learning algorithm is going to come in. It's going to take in a set of images and produce a set of scores, or something of this point. And the way we're going to order it such that larger ST means that it's going to be more likely that there's a change point. Okay, so we'll get later to how to design such an S. What is the optimal S? How should we design it? We'll get to that later. But that is an input to conch. We have to come up with a score function. The second piece of notation is what I'm going to call a split permutation group. So the split permutation group, pi t, what it does is it's the set of all permutations over all n indices that does not permute across t. So it actually permutes 1 to t amongst itself, and it permutes like t plus 1 to n amongst itself, but it doesn't permute across them. Okay, so permutes kind of independently between left and right. So the set of all permutations which maintains this property is going to be called pi t. Okay, so you have the set of all permutations, which is Sn, like that's n factorial permutations, and some subset of them respects the structure of a particular index t. So pi subscript t is just the set of those. Yeah.
If I understand correctly, that ST is actually a n-1 dimensional vector. How do we compare the larger SN?
Or just the so the teeth element of S is an n-1 dimensional vector, and the teeth element of S is the score for the teeth point.
I see.
And it's larger means it's more likely to be. So you get back a vector of scores. The large scores are where the change point is likely to be. That's kind of what you should intuit the score vector as being. Okay, so these two are inputs. You have a score vector, which is a function. Sorry, a score function. You have a score function, and you have this split permutation group, which is just notation. So the p-value is very simple. Okay, this is what it is. It's 1 over the size of pi t. I'm averaging something over pi t, and I have a sum over all permutations in pi t, and I'm going to look at the score if I feed into S the permuted data set pi of x1 to xn, and compare it to the score when I feed in the original data set x1 to xn. Okay.
Wait, a clarification question. So ST output is a scalar, right?
No, S output, yeah, ST is a scalar. Yeah, S is an n-1 dimensional vector. ST is just its teeth component of that vector.
Just remind me why it is -1 rather than n.
Oh, because there's only n-1 possible change points.
Okay.
If it's n, then there's no change. So the change point is, so like 1 to psi is from the first distribution, and then psi plus 1 to n is from the second distribution. So psi only has to be 1 to n-1. That's why. Okay, so anyway, so this is the p-value. I mean, that's the claim, at least, that it's a p-value. But for now, it's something you can calculate. You look at all permutations that permute separately on the left of t and separately on the right of t, and you compare the score for the permuted data set compared to your original data set. And the intuition is that if t is the actual change point, if it magically, because you're going to scan over different t's, one of those t's is actually psi, you don't know which one. But when you actually are calculating peak psi, then you are permuting data to the left of psi and you're permuting data to the right of psi. But those were IID to the left of psi and they were IID to the right of psi, and those permutations do nothing. Okay, and so then the rank of that object will be equally likely to be smaller or larger than the original score. Like the score on the permuted data set and the score on the original data set are likely to be exchangeable. So this p-value is going to actually end up being a uniformly distributed. So it's a very simple idea, but that's kind of all you do. You calculate this p-value, and then you just report the confidence set as the set of indices for which the p-value was large. Okay, so it's very simple. And the theorem is, as claimed, conch yields a non-asymptotically valid, distribution-free 1 minus alpha confidence set for the change point psi. And the proof actually of that is literally, like, to show that it's valid, you actually only have to argue that of what's happening at psi, because it's not valid if you kick out psi, if somehow psi was not in the set. So and it is valid if psi is in the set. So you only have to argue what happens to the peak psi. You really have to argue about that. And it's very easy to argue that peak psi is uniformly distributed because it was independently permuting things to the left and the right, but things to the left and the right were exchangeable anyway, so permutations didn't do anything to them. And so there you get this kind of uniform p-value from that. So the proof is actually very straightforward. And if you think that this is not computationally feasible because there are still a lot of permutations, like there's for any t, there's in pi t, there's t factorial things to its left and maybe n minus t factorial things to its right, whatever. So there's still a lot of permutations to do. So you don't really want to permute over everything in pi t. You can just do a Monte Carlo version of that, which is you sample uniformly from this pi t, and you can do that independently on the left and the right. Like to sample uniformly, you can just take a permutation for the left part and a permutation for the right part, and calculate a p-value using like m as 500 or something like that. And this does not affect the finite sample validity at all. So this is still a finite sample valid p-value, and the confidence set is still finite sample. So we'll call this the Monte Carlo version, but it still works.
Is there a formal assumption on the S for this?
No, for any score S. So the efficiency of the set, the size of the set is affected by S, but for any S, this is actually still valid. So there's no assumptions on S. So there's no assumptions on X, the space of the data, on the distributions, on S. Yeah, it's very clean. And we'll get to now the efficiency part of it.
It's kind of similar to the non-common score.
Yeah, it is similar, but here it actually, you have to still construct
So
it differently.
break the exchangeability is still, yeah.
Yeah, but we'll see some critical differences actually on the next slide. But I'll take a question and I'll show you an important difference next slide.
If you compute P for all time steps, do you also have to take care of like a union form?
No, nothing. You just compute it separately for each step. So for each t. That's the magic of confidence sets via inversion from p-values. It's just you calculate each p-value as if no other p-value existed, and then you don't have to correct for multiple testing. Because there's actually only one null. So that's the magic. So actually there's n things you're testing, but there's only one null that's true. That is peak psi is the only, like, the hypothesis for psi, that's the only null amongst them. So usually you have to correct for multiple testing if the number of nulls are unknown, and you have to correct for that. But when you actually know this exactly one null, then actually the inversion does not need to correct for multiple tests. So good question, but luckily we don't need to.
Yeah, so following up on that question, so you said your method can construct sort of like a uncertainty set for the side.
Yeah.
So I assume what you do is that you calculate this P for each time step.
Correct. Yes.
And then
For each t, we calculate this pt, right? For each t, we do that. We have p1 to pn minus 1, and then we just keep the set of indices for which the p-value is larger than alpha. That's it.
Oh yeah, and randomness. So I was wondering if this is like, do you have to do any corrections?
No. No, that's it. You don't have to do any corrections. Yeah. This is, I mean, that part, the inversion from p-values to confidence sets, that's just standard statistics. So like everywhere in statistics, you construct confidence sets by inverting tests, and there is never any correction. And so here also there's no correction. There is no factor of n or Bonferroni or nothing like this going on here. It's like every test is level alpha. As n tests, they're all done at level alpha, and then you form the confidence set by inversion. Yeah. That's the slide like 5-6 slides from now. Yeah. So we'll talk about multiple change points soon. Yeah.
Do we have some intuitive guarantee that the confidence set is just going to be one interval, or can it be multiple?
It can be a union of intervals, but we'll see in experiments and practice it's usually an interval, and we can control its size and stuff. I'll tell you about its size soon. Okay, all good questions. Any other clarifications? Okay, so this set that I presented on the previous slide is really a 1 minus alpha distribution free confidence set for psi. Okay, so here's an amazing result, universality. Every distribution free change detection procedure can be recovered by conch using some score function. So this is not just an algorithm for distribution free change localization. I should have said localization, sorry, if you'll allow me. This is easier for me to do now than for me to remember to do later on. Okay, so every distribution free change localization procedure can be recovered by conch using some score function. There's no other procedure. It's not like tomorrow you'll come up with a smarter procedure that will do better. Conch is it. The only thing you can change is really the score function. So that's pretty nice. And you can also wrap conch around any heuristic method. So maybe you have your own favorite method, like maybe using a bootstrap or something like that, that produces some kind of asymptotically accurate confidence set, or under some parametric assumptions produces a confidence set. You can use conch as a safety device. So essentially saying, well, I would like to protect myself against violations of whatever underlying assumptions are needed. And so here's two examples of that. This is the same type of p-value plots with n. The left is just some based on some Gaussian and Laplace data, because the bootstrap is known to asymptotically work in certain simple settings. And so the orange curve is actually the bootstrap curve or the p-value curve. If you want to look at the confidence set, you can threshold at any level like 0.05. That will give you the confidence set. And then if you take the p-values from bootstrap and you construct the score function using those p-values and you feed it through conch, you actually get the blue curve. So in this case, you can see it becomes significantly tighter. But more importantly, whatever comes out at the other end of conch is non-asymptotically valid and without any distributional assumptions. But for the bootstrap around it, it is usually asymptotically valid and usually under some regularity conditions, which we don't need either of those. So you can think about conch as either it's a standalone change localization method or it's a wrapper around your favorite one that protects you in case your assumptions went wrong.
What do you mean by the wraparound again?
Wraparound, meaning that, so I presented conch as you wanted to change localization, you use conch. But some people might have their own favorite algorithms that they like to use. You can wrap conch around that. You can first do your favorite algorithm like bootstrap, and then you can take the output of bootstrap and feed it through conch
As the
score. So basically, you can use the p-values from the bootstrap to construct the score function.
and
I didn't put it on the slide, but in the paper it's described how. And then you use conch with those score functions, and then what comes out will be distribution-free, non-asymptotically valid.
And I would imagine that better the score.
Yeah.
Smaller the set.
Correct, exactly. But it's corresponding to the set, yeah. So these are pretty good scores that bootstrap feeds into conch, which is why conch improves it. So this is technically, yeah, conch on top of bootstrap. Okay, so now the score function. How should we use the score function? So obviously, so good and informative scores means you get high power for the tests, which means you get narrow sets when you invert it. And so the scores are really important outside of Xi, because at Xi, whatever score function you use, it's a uniform p-value. So it's really for the points outside of Xi that you care about it. Now, if you want to think about general testing where you're testing, let's say you're testing a point, is t the change point? And suppose t is not actually Xi. So let's say Xi was 400, your testing is 5 the change point. Okay, you're testing that. Now, if you were testing that, you can ask yourself a hypothetical question, which is, what is the best way to test is t the change point against, let's say an oracle knows that Xi is the change point, and let's say they test it against actually the alternative being Xi is the change point. And the answer is, well, I should use like a likelihood ratio, and the Neyman Pearson lemma will tell you that the likelihood ratio gives you the optimal test. But in our case, we can't directly use the Neyman Pearson lemma because we are constrained to use conformal p-values. That's what we have to use. We don't get to use a different test. Our p-value has to be a conformal p-value. I have to choose a score function. I have to do these permutations. That's how I have to calculate it. So it's not obvious that the Neyman Pearson lemma applies because I'm kind of in a more constrained setting, having to use conformal p-values, not just any p-values. So to construct the optimal score, here are just two observations before I present our version of the lemma. The first observation, which makes it differ from a conformal, there was a question, is this like a conformal score? It's not, because scores that are symmetric in the data are actually completely powerless. So if you look at the formula for the p-value, if the score function, it takes in a vector of data and outputs a vector of scores, if it treats the data as a bag, then actually it's a powerless score function, because it will give you the same answer on pi of x as on x, and in which case this inequality will always be true and the p-value will just be 1 and you will get no power out of it. And so essentially in conformal prediction, we usually use score functions that are symmetric in the data. That's the usual conformal scores are symmetric in the data. They're given feed-in data set, they process it using some machine learning algorithm that treats it symmetrically usually, and so on. So, but this kind of, so it's intuitively different from a conformal score function. So, which is why we call it a change point plausibility score function, because it's qualitatively different. And then a second observation, actually, which is not hard to prove, is what I call a data processing inequality. in this, if you swap S for f of S for some non-decreasing function f, then we can only actually make the confidence set larger. So post-processing of a score actually is a bad idea. It will always hurt you. So with those two kind of at the back of your mind, the conformal Neyman-Pearson lemma we're able to show is that even though we want to derive a conformal p-value, the optimal score function is still a likelihood ratio. It's actually the it's a likelihood ratio of the data before t, the data versus the data. I mean, you take f0 for the data before t and f1 for the data after t if t is the change point, and it's f0 before r and f1 after r if r is a change point. So if you were comparing t to r, but you're forced to use conformal p-values, the likelihood ratio is still the optimal score function. But the problem to apply this, of course, is that I don't know f0 and f1. I don't know the distribution of the data and so on. And of course, I don't know r either, which is my competitor. So there's few natural things you can do. One is we know that likelihood ratios, we're using a classifier trick, classifiers log likelihood, approximate log likelihood ratios. And so you can instead train a classifier and use that as a proxy log likelihood ratio. I mean, taking log doesn't matter here because that indicator function is, if you apply any log to it also, it's the same indicator. So it's log of st less than log, doesn't matter. So increasing functions, if they're strictly increasing like log, they make no difference whatsoever. So you can think about learning a classifier that approximates the log likelihood ratio and using that as your score function. And since you don't know the alternative, again, you can use some kind of a heuristic, like maximum likelihood or some heuristic method, even with proxy non-parametric likelihoods, to pick an alternative R that you want to compare against. So the key point in all this is that the score function, the choice of the score function doesn't affect validity. So how you learn, did you learn it perfectly or not? It can't hurt validity. Once you plug such a score function, even if approximate, into const, it gives you validity straight away. The validity is for any score function. And so the score function is mainly useful for making sure that they're informative sets that you get out, and so they're small. And so yeah, what we have been using is just off-the-shelf black box classifiers and so on. Okay, so what can we mathematically prove about the size of the sets? So just just 2 slides about statistical efficiency of the sets. This is about asymptotic consistency or efficiency. So here we put ourselves in a what's called a triangular array framework, where instead of having one problem, I actually have a sequence of problems indexed by n. Okay, so I have n points, and as n goes to infinity, I'll give you some guarantee. And so I need 2 assumptions. The first one is that the change point is not at an extreme. Okay, so the change point in the nth problem is denoted xi n, and xi n by n converges to some constant between 0 and 1, like 0.4 or 0.7 or something. But it's away from the extremes, because if the change point really occurs at in the limit at one end, I really can't expect to find it, because it's as if I'm observing all the data from one distribution. So how am I going to find where was it at this end or at the other end? I almost have no data from there. So the first one is that it's a non-trivial change point, which I think is a reasonable assumption. And the second one is that the log likelihood ratio. So I don't know the distributions before and after, but those distributions exist. Let's say the log likelihood ratio has a finite variance under P0 and P1. Okay, so this is just saying that anyway, some kind of a very mild regularity condition. And then, so the first slide is if you use the Oracle score. So Oracle score is using the conformal Neyman-Pearson lemma. It tells you to use a score. If you were an Oracle and use that score, then the size of the set is order 1. So I have n, it's of size n, my data points of size n, but my set is only of size order 1. So OP1 is the improbability version of order 1. So it's a constant size. Another way of saying it is the relative size of the set. If I divide by n, is 1 over n, it's vanishing. So I'm going to get a set that's, if I always think of my points as my change detection problem as being on 0, 1, if I always rescale to 0, 1, then the confidence set is rapidly shrinking in size at a 1 over n rate. That's for the Oracle score. So you can ask, well, what about if you learn it? And so under one more, I would say, relatively mild condition, if you can learn the log likelihood ratio in the squared norm. So if you have a method that tries to approximate the log likelihood ratio, for example, using classifiers or using kernel density estimates or something like that. So if you have a way of learning the log likelihood ratio asymptotically, in the squared norm. That's the third assumption. Then actually even for the learned score function that you learn from the data, you get the same type of, similar type of guarantee that at least the size vanishes in probability. Okay, so just a couple of, you can prove consistency of the point estimates, consistency of the confidence sets that they are shrinking and vanishing and so on under what I would call very mild assumptions. So validity you get always, and statistical efficiency and sharpness you get under mild assumptions. Okay, so a few more experiments. So here's, I showed more complex ones, but let's just look at a simple one. This is Gaussian mean shift detection. So at time, again, 1,000 data points, at time 400, it switches from normal -1, 1 to normal 1, 1. And then here's 4 versions of conch with different scores. The first one uses a kind of a weighted mean score. The middle one knows the distribution of the data and uses the Oracle log likelihood ratio score. And then this one says, I know it's Gaussian, I'm only going to learn the mean. So that's what par learned means, parametric learned. I still, let's say I assume the data is Gaussian and I learn the means, but then I plug that learned score into conch. Okay, so I still use conch because I want to protect myself against a bad assumption. And then this is non-parametrically learned like log likelihood ratio. There I don't even assume that I know it's Gaussian. I use kernel density estimation to learn the log likelihood ratio. And so you can kind of see that, even though the Oracle does super well, but our learned versions of it also do really well. Here's a different example where CIFAR class change, it changes from bear to beaver. It's actually not that easy. If you look at some of the images, they are a bit blurry actually, and you can't really tell on the right, is that a bear or a beaver? I don't know. So anyway, so that's we looked at that, and then we trained the three block CNN, 2 types of training. Week 1 is we only trained for 5 epochs, just to show the effect of the quality of the machine learning algorithm that you're plugging in. The strong one is we tuned it for 20 epochs. And you can see on the left, this is the full time scale, and you can see the difference between the conch, which is using a weak classifier, versus conch using a strong classifier. They're both pretty accurate, but if you zoom in to the relevant region, you'll see that conch with a weaker classifier gives a wider region. And if you have a stronger classifier, it gives a narrower region. So, seems reasonable, pretty accurate. Here's a version with language. So this is sentiment change. This is from Stanford Sentiment Tree Bank. So basically, again, 1,000 phrases, sentiment phrases. This is about some movie reviews. And so the first 400 are positive reviews, like they contain phrases like juicy writer, intricately structured and well-realized drama. And then the rest of them, 401 onwards, they consist of words like painfully or gratingly irritating films, things like that. Anyway, so we don't know how things have changed. We don't know. We just have a sequence of, we have text phrases, and then we want to use language models to know if there was such a change in the sentiment. And then you can see that it's really quite sharp. Now, if the plot on the left is if there's a pure shift from all positive reviews to all negative reviews, then it's super sharp and gives you a very tiny confidence set. But if you have a mixed shift, which is from 60-40 positive and negative reviews before time 400 to 40-60 positive negative reviews after time 400, then you get a slightly wider confidence set. So again, this is just trying to show you that if there's more noise in the data, of course, your confidence set is going to be wider.
What's the score function here?
It's just like from classifier based. Maybe you remember the score function exactly.
Classifier based, you have the not given by font, so classifier trains that so long like it estimate. Just
The classifier is just like simple.
Okay.
Yeah, pre-trained. Yeah.
Another quick question. So if I understand correctly, you're conducting an experiment in an offline setting.
Yes. Everything that I'm presenting today is offline.
So I think first of all,
I have like actually a separate line of work doing sequential offline
So
localization.
because I wonder if more practically people use Changepoint to action in online setting, right? If you want to data stream and you want to visualize.
Yeah, both occur actually.
Well, of
They
course.
both do. Yeah.
I just wonder how would possibly apply this experiment in online setting, because in online setting, you kind of look back, right?
Yeah.
It doesn't make sense to quantified uncertainty with the set, more like if you only care about the lower bound.
Yeah.
Of the,
Yeah, so I mean, I would say wait for a few months. I have a couple of parallel preprints that are not out yet, but which I try to address this problem. Actually, I've been interested in this problem for a long time. For the sequential one, yeah, but there's some subtleties there because usually there's you're running a detection procedure, which is a stopping time that says I'm monitoring the data, and then at some time I say, oh, I think there has been a change. Now, the thing is that typical monitoring procedures can have false alarms too, and so you have to actually you have to define the confidence set correctly, which is conditional on stopping after a change. So you have to ask property that I have containment condition that I stop after the change is at least 1 minus alpha, and yeah, some slightly different ideas are needed for giving the sequential guarantees, but yeah, these can be adapted, but maybe if I'm back in a few years, I'll tell you about that version. Okay, and then someone asked about multiple change points. So now it turns out that like independently of our work, like people have looked at multiple change points in the literature, and they're even just often even just for point estimation. And what they do is they first try to segment the data into blocks in which there's one change point. This is kind of just like they try to reduce the problem. They try to first do a segmentation algorithm, and then within the segments they try to do one. And so roughly what we say is we don't have any guarantees there right now, but there are many well-known like segmentation algorithms. And so if you take one off the block, your segmentation algorithm, and it gives you certain segments, then I mean it won't give you segments, it'll give you guesses for where the change points are. So then what you do is you form the segments by taking the midpoints of the estimated change points, and you run conch within those segments. And so let's say that you have a segmentation algorithm that returns guesses for some number of change points. You don't know the number of change points, even the number is estimated and the points are estimated. So then you just take, so if it says, I think there's one at 100 and at 200 and at 300, then you say, let's run conch from 0 to 150. Let's run conch from 150 to 250 and so on. And then hopefully it'll give you, if you really did isolate a change point, it'll actually give you correct confidence sets there. So empirically, this is what it looked. I mean, we just did some simple simulations for this, and so here there's 4 changes. We don't know it, and the algorithm doesn't know it, but the algorithm provided some guesses for the change points. Like maybe so these are the true change points. Actually, sorry, the blue lines are the true change points. These were some estimated change points, and then we used them to form blocks and run conch, and then conch gave this p-value plot. And so anyway, so you can, as long as the first step is correct, it's somehow conditional on that the second step is correct. But I don't know how to do the first step in a completely distribution free way. We have some ideas for that, but it's not out yet.
Yeah, along these lines, suppose we commit to having a single change point.
Yeah.
And we could even have a data set that looks like this, and perhaps it's got some kind of latent structure. I think it just makes it kind of spiky. But it still has finite variance, which is I think kind of the only main condition on the moment. Wouldn't we get like somewhat disjoint sets? Like basically it would look something like this, even if we had a single change point detection.
Unclear. I don't think so. It might give something like random in the middle also, because it's only looking for one. Yeah, I think the question is, will it have spikes? It will only have like this spike somehow exists because I'm only looking at this region and I'm permuting data here and here. Now, if I had the whole data set and I was looking at this p-value and I'm permuting all the data here, it would depend on what all the data looks like compared to this data. So if this data was actually very large, let's say the changes were large, smaller, 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 then actually it would be okay, because here it's large and here it was smaller, but when I average everything, it's still even smaller, so then it's okay. But when I'm averaging all of these things, it actually looks similar to the left, then I won't detect that change point. So I mean, the answer is that you'll get something, but in different, it's not clear that you'll get spikes. Sometimes you'll get spikes, sometimes you won't.
We can handle one, say, depending on the spikes, or rather, if we have an model that tells us how some kind of contrast of how big the fake spikes versus the real spikes are.
Yeah. I mean, right now, I don't have any guarantees in this setting, but we do have an idea for trying to get a distribution-free estimate for k hat, like for k, the true number of change points. We have some ideas on at least getting a distribution-free lower bound for k, but that's still ongoing work. Maybe those that can be used along with conch in some interesting way. Yep.
For single change point localization, is there any like guarantee about the distance between P0 and P1?
No.
The size of the set?
No.
Like it's not possible to do that at all.
No, there's no assumption. It's just the different.
No, but like, can there be any guarantee that if P0 and P1 are closer to each other in terms of the distance,
Yeah.
the set is going to be wider?
I mean, this is true.
Yeah.
You'll have you'll have that behavior,
Yeah.
but it's not in the leading order term, meaning you'll always get this kind of 1/n like size of the set, regardless of P0 and P1, but the constant term will involve some kind of distance between them. It doesn't affect the rate, it affects the constant. Yeah.
Single change point name again, like theoretically, there is no constraint on where to change exactly.
Exactly, that's right.
But they tested it very quickly because I saw everywhere it was 400. So
Yeah, I mean, we like it just should not be in the first 25 or the last 25. Yeah, I mean, if it's even at 100 and 900, it works fine. Yeah. And in fact, that's the guarantee is that I mean, basically, as long as in this sequential setting, it has to just converge to anything between 0 and 1. Practically, what that means is effectively you're not in the. I mean, yeah, just not right at the ends. It does work fine. Yeah.
Also, is this sharpness result, is that some kind of fundamental bound or is it kind of dependent on you, like your underlying algorithm converting with some sample complexity and?
So firstly, this Oracle score is actually very sharp. I mean, it's very, very strong. It's basically telling you out of n points that are there, your set size is constant. I mean, the lower bound is constant. You have to have at least one. And your set size also has constant size in probability, which is very strong result if you use the right score. And well, I guess depending on what type of assumptions you want to put on the learning, if you put stronger assumptions on the learning, you'll get stronger guarantees out of it. But yeah, I mean, we have a few variants in the paper.
So this is the weakest possible guarantee for any learner.
Yeah, exactly.
You have like n factorial sample complexity for my underlying.
Yeah, you can't hope to do better than this. And yeah, this already achieves some sense how well you can do. But the bottleneck here is learning. You can change a little bit of the learning and get slightly different guarantees, but at least we know that if we had the right score function, this is just amazing. Yeah. Okay, so that's all I have. So let me just summarize very quickly. We introduced Conch, a conformal p-value based framework for offline change point localization. It offers finite sample and distribution free guarantees. It produces shrinking confidence sets for appropriate score choices. It is universal in the sense that every algorithm that produces a distribution free confidence set is actually just an instance of Conch, and it can be used as a wrapper around your existing methods if you have them. To provide some kind of protection against violations of your assumptions. Okay, so with that, let me thank all of you and happy to take any more questions.